much easier. And that's what Colin Mclaurin figured out is, okay, this is much simpler if we use 0. It's a lot easier to wrap our brains around. But basically, if sorry, one sec, something on my computer's acting weird. If this will, again, kind of our assumption to begin with is, whoops, got the wrong pen out. Our function f of x, which is e to the x, so I'll just write that. E to the x is our function. It will have a power series. We're going to assume that it has a power series representation. And that means that it, in some form, it will have, it can be written as some series of coefficients multiplied by x to the n. And basically, we're gonna center it at 0 instead of at a. And so I'm just gonna write Cn x to the n, a general. Basically, this is just a general power series where we have the series of coefficients. But basically, we already know what Cn should be. That was the point of the derivation, is we have solved the series of coefficients for any function. Literally, any function will all have the same pattern behind its power series representation. And that will be the nth derivative evaluated at the center divided by n factorial. So basically, if I want to know what is e to the x's power series, we can just use, this is what's the general Maclaurin series formula. And if you ever are trying to figure out one for yourself, just start with this. This is the formula for solving its Maclaurin series. But basically what you need to do is you need to figure out what is fn at 0, because everything else is known, right? We know that it's the nth derivative evaluated at 0, and n factorial and x to the n, those are consistent regardless of what it is. But basically, so what we need to consider is, what are the consecutive derivatives? What is f prime of 0? What is f of 0? What is f prime of 0? What is f squared of 0? Or not f squared, f, the second order derivative, and so on. But if we're going to elaborate this, right? So the expansion, and also on your packet, I've provided the general formula for a Maclaurin series, as well as the expansion, because the expansion of Maclaurin series will always look like this. But basically, e to the x, it will look like f of 0 plus f prime of 0 times x. Sorry, but basically, every Maclaurin series will look like this. This is the formula. Let me highlight it. Sorry, there's so many formulas that we've gone through today. But basically, if you're trying to develop a power series for any function, it will be this. This will be its Maclaurin series representation. And again, we're going to use Maclaurin because, again, if we're looking at the difference between a Taylor and a Maclaurin series, it's just so much simpler. But basically, the first coefficient will be f of 0. The coefficient on the degree 1 term will be f prime of 0. The coefficient on the degree 2 term will be f double prime of 0. Basically, you take the consecutive derivatives. Now, one thing that's kind of easy to forget is that, with the first 2 terms, it's literally just the intercept of the polynomial and in its derivative as the first 2 coefficients. But the third coefficient, you need to divide by 2. The fourth coefficient needs to be divided by 6. And so on. Sorry, let me erase this. And, then I would have the fourth order derivative of 0 over 24, and so on. But basically, if I want to solve E, I need to figure those components out. The coefficients, what is f of 0, what is f prime of 0, f double prime, f triple prime, and so on. So, well, E, it's spectacularly easy because E, if we look at its derivative, right, f of x is e to the x. If we take the first derivative of e to the x, the derivative of e to the x is always e to the x, right? So consecutive derivatives, the second order derivative would be e to the x, and so on, right? It's the only mathematical function whose derivative is equal to exactly itself. So if we're looking at the pattern of the Maclaurin series expansion, it will be consistent across the board. And if we look at, well, again, f of 0 is all we need to do is plug in 0 into that. Well, that would be e to the 0. And remember, any exponential, if you plug in the exponent of 0, is always 1. Anything to the 0 makes 1. And similarly, f prime of 0 will be e to the 0, which is 1. And what you can see very easily is that every consecutive derivative of the function evaluated at 0 is going to be 1 for e. So f double prime of 0 will be 1 because it's the same all the way through, right? Another way we could write this is the nth derivative of e to the x is e to the x, and therefore the generic fn evaluated at 0 is 0. And why that's kind of a useful way of writing it, by the logical conclusion of these patterns that are quite obvious once we look at them. But basically what this is saying is that for e to the x, the nth order derivative at 0 will be equal to 1. So if I highlight that, basically this right here is always going to be 1. So for e to the x, so specifically, let's go ahead and write that solution. E to the x is equal to the summation as n goes from 0 to infinity of 1 over n factorial x to the n. Or, not x squared, x to the n. Or the way that I usually write this, when I write E's Maclaurin series representation, is like this: x to the n over n factorial. So basically, this is the formula that we just figured out, we just derived, which is that e to the x, if it will be an infinite series, its series of coefficients must be this. And that's exactly what this sheet says. If you go back to the cheat sheet, which will be provided on the final, or what I call the established Maclaurin series, e to the x is given by this. And so the last thing is regarding this is that you don't need to memorize all of these proofs. When we do them in class, my goal is to show you guys where all the math comes from, so that it makes as much, that makes sense, and that we can kind of understand how people figured this out, where it all came from, right? And essentially the patterns that allow us to determine these. At the end of the day, anybody could go look up these formulas and use them. But in general, most people don't really understand these formulas because they're quite complicated, right? It's an infinite series involving x, right? These are very complicated mathematical expressions. And our goal is to really understand infinite series, and specifically power series and Maclaurin series, which are just a special type of power series to represent a function. Or if we look at the expansion, right, if we plug in those values, what I would just have is 1 plus x plus 1/2 x squared plus 1/6 x cubed, because essentially the nth derivative evaluated at 0 for e was always 1. So basically what that leads us to is the coefficient is always 1, or technically 1 over n factorial. And this expansion gives us e. And so the last thing, the very, very last thing, I know I keep saying that we're almost to the end, is let's look at the visualization. Because again, basically this math, it can seem very strange, and how it seems like we're doing a bunch of crazy made up stuff if you just look at the formulas. But let's look at, which again, posted on our canvas, let's look at the GeoGebra representation of this, and then we can see it in action. Again, I really like to look at the graphs of these, which I created a few years ago. But if we look at the beginning here, notice that what it says is the first term of e is 1. Notice actually the first couple terms are exactly the same as 1 over 1 minus x, which is kind of interesting. But as we progress, the thing that's different about them is the coefficients. Literally the only difference between the different representations is the pattern of the fractions, which is why all of the convergence of these random fractions series is so important, right? We've been studying all sorts of random series for weeks, and this is really one of the main reasons why they're so useful, and why we need to learn all of them. But anyways, starting with the first term, it starts with just 1, right? Here we have e to the x in green, a general exponential function. And we have in blue just f of x equal just a constant function 1. If we add in the second term, we're going to have now 1 plus x is exactly the same. It's just a linear function, slope 1. It's connected to e to the x at the exact same point. Again, notice they overlap on the intercept. And as we add more terms, again, notice that we have now 1 plus x squared over 2. Now it's slightly different because the parabola is a little bit down from where it was. The slope is different. And really, we found the coefficients by looking at the slope, looking at the concavity, looking at all of the derivatives and how those line up. And then if we continue with third order derivative, fourth order derivative, fifth order derivative, notice that as we continue with these patterns, it fits precisely with e to the x. Now let me just play it through generically, but I find it very fascinating that as we add more and more terms of the polynomial, again, notice it can never be exactly an exponential function, right? Because a polynomial always has to go to infinity. An exponential function goes to 0. But if we bring in more and more terms, it looks sort of like we're wrapping it around, or we're sort of tying a thread around it. But if we keep tying that thread forever, eventually we're going to get exactly that function. The only time they won't add up is if we ever stop in that infinite expansion. So let's just do it one more time. Starting at the beginning, if we go 2, 3, or 4, or 5 terms, it starts getting closer and closer, and that is the fundamental idea. What we'll talk about in class, the next couple of classes, is you can actually, this is how a lot of calculators work. If you ever wondered, like if you take a calculator and let's say you did e to the 0.67 power, how the heck does a calculator know what e to the 0.7 power is? How does it figure this out? But basically, you can use these power series to do more than just calculus. You can do all sorts of stuff, and a lot of calculators rely on this mathematics. It's very fundamental. And if you're a computer programmer, it's very important to understand that functions, instead of using, there's always an alternative representation. There's a different way of calculating values, which might take some intense math to figure out, but at the end of the day, if you can kind of see, let's say we look at e to the 0.7, which would be right here, it's virtually indistinguishable, right? Blue and green, if we use enough terms, will look the same. So say we use 4 or 5 terms in the Taylor series, it would be enough to do the calculation. And finally, I can demonstrate this. So let's say we started with 1, right? That would be the first term in the expansion. Now, basically here I have e to the x, right? E to the 0.7 was what the calculator did. If I add the next term in the expansion, now let's say I add in x, well, that would just be plus 0.7. That would be 1.7. And if I continuously add in more and more terms, as I add those terms, it will get closer and closer to e to the 0.7. So the next term I would need to add is plus 1/2 times 0.7 squared. But basically, I can use arithmetic to calculate the value of e to anything. It's a very, very interesting idea. Then the next term would be plus 1/6 multiplied by 0.7 cubed. Now, notice it's very, very close it's getting very, very close to that value of e to the 0.7 that the calculator spit out up here, 2.01. We're not quite there yet because we don't have enough terms. But essentially, once we get enough terms, that's the last part of the lab. For lab 11, I ask, how many terms do we need to get an accurate answer? And that's always the case with a series. Technically, you want an infinite series to get an exact answer, but practically speaking, right, at some point we have to use, there's only, maybe 4 or 5 terms, however many terms we need to get an accurate answer. And so if we add one more term, the next term would be 1/24 times 0.7 to the 4th. But basically, as we do that summation, notice what we're calculating is the value of e to the 0.7. And it can kind of seem like magic, and notice we're off by about 1,000th here. But, if we keep adding more and more terms, it will eventually add up to the true value of e to the 0.7, which is given by an infinite series. Basically, there's a numerical representation for any e to any power is going to be given by some infinite series. And if we plug in x, we can calculate that value. And similarly, integrating and differentiating, very easy to do, which needs to be done for the lab. So anyways, I'm done. Sorry, lab went for so long for today. I will post this on Canvas as usual. If you want to, if you need to go back and watch it, or if you had to miss any parts or anything. Anyways, see you all in class tomorrow. That was the last lab of the semester, so I don't feel as bad for talking for so long. But yeah, again, lab. Let me know if you have questions on the lab final. I'll be hanging out here for a little bit. Have a nice rest of your Tuesday. Hope you all had a fantastic Easter. And we are almost to the end. See you tomorrow at 8:30. Let me know, email me or anything if you have any other questions that can't think of right now.